The Great Pacific Garbage Patch is roughly 3 times the size of France and holds up to 100 million kilograms of plastic. You cannot just sail in and scoop it up. The debris is spread across thousands of square kilometers, and most of it is now broken into pieces too small to see. Stopping this takes machines operating at a scale ocean cleanup has never tried before. And even after recovery, the harder problem is what comes next. In this video, we walk through every link of the chain. Plastic ocean pollution is a dispersal issue. Waste spreads across vast areas like the Great Pacific Garbage Patch, instead of forming one removable mass. What makes dispersal dangerous is that plastic does not degrade. It just keeps moving. Even waste lost far offshore can return through beaches, tides, and marine ecosystems years after it first entered the water. Over the next few minutes, the path of ocean plastic becomes visible, from crowded rivers to offshore recovery zones. More plastic was removed from oceans and rivers in 2024 than in all previous years combined. Large-scale cleanup systems operated across the Pacific, while interceptor barriers blocked floating waste before it could drift into open water. Crews recorded more than 11,000 tons of collected debris across 112 extraction runs in the Great Pacific Garbage Patch alone. New interceptor deployments expanded into Thailand, Jamaica, and Guatemala, where the largest barrier installation began protecting waters connected to the Gulf of Honduras. Several coastal communities now depend on these systems to reduce flooding risks during storms. One successful cleanup still leaves endless streams of new debris moving toward the sea every day. Progress is real, but the debris keeps moving faster than the cleanup does. Plastic pollution rarely stays concentrated long enough for easy collection. Across rivers, coastlines, and offshore currents, floating debris spreads into thin-moving layers that are difficult to track consistently. Some sections of ocean can appear completely clean until sunlight catches tiny plastic fragments just beneath the surface. During 2025, cleanup crews expanded interception systems while researchers mapped plastic movement using automated imaging and river survey tools. More than 25 million kilograms of waste were removed from aquatic environments that year alone. The challenge is no longer proving plastic pollution exists. The harder task is locating fragmented waste streams before tides and currents scatter them even farther. You can scoop a bottle out of the water. You cannot scoop out what the ocean turns it into. During a 2.5-hour aerial survey above the Great Pacific Garbage Patch, crews spotted more than 1,000 large plastic objects drifting offshore. That visible debris is only part of the problem. Waves, salt, and ultraviolet exposure slowly break larger pieces into microplastics, smaller than 5 millimeters. And around 51 trillion microplastic particles now drift through the world's oceans. The shift from debris to microplastics changes the threat entirely. Once plastic crumbles below 5 millimeters, it moves through ecosystems, into fish populations, and eventually into human food systems. 5 massive ocean gyres spread floating debris across thousands of square kilometers, turning cleanup into a logistics operation involving ships, fuel, transport, storage, and waste processing far from shore. The farther trash drifts from rivers into open water, the more expensive every single ton becomes to recover. If cleaning plastic from the middle of the Pacific is too expensive and too late, the real question becomes, can it be stopped before it ever reaches the ocean? Stopping trash in a river sounds cheaper and simpler than chasing it across an ocean. But first, you need to understand what you are actually up against. The Rio Motagua in Guatemala is a case study in how a river becomes a pipeline. Guatemala City sits at the headwaters. Most of the country's waste gets hauled to a landfill at the edge of the city, which sits directly above the Rio Las Vacas, a tributary feeding the Motagua. When rain hits, runoff carries trash off that landfill into the river. Communities along the banks with no waste collection do the same. Illegal dumping adds more. A hydropower dam catches some of it until floodwaters overtop it and the whole mass runs downriver. At the confluence where the Las Vacas meets the Motagua, the water arriving from upstream is already unrecognizable as a river. What reaches the Caribbean coastline is not just bottles and cups. It is toys, shoes, styrofoam, cutlery, soap dispensers, a complete cross-section of daily life. An estimated 10 to 30 million kilograms of plastic moves through this single gorge every year, roughly 1 to 3% of all plastic entering the world's oceans. The Motagua itself, upstream of that confluence, runs clean. The pollution has a precise starting point, a clear path, and a measurable endpoint. That means it also has a place where it can be stopped. Intercepting plastic mid-river is deceptively logical. Trash is still concentrated, still floating, moving through a measurable corridor. Jakarta made that case undeniable. Plastic choked every drainage pump in the city, visible in streets, canals, waterways. Despite constant cleanup crews, the Interceptor targets two problems simultaneously: keeping plastic out of the ocean while relieving Jakarta's collapsing drainage system. An angled floating barrier, not a dam, uses the river's own current to herd surface debris toward the machine's intake. A perforated conveyor then lifts waste clear of the water. The holes matter, draining water back through, so the mechanism isn't crushed by unnecessary weight. Collection bags fill, swap out, and head to shore. Powered entirely by a 12.8 kilowatt peak solar array, with 50 kilowatt-hours battery backup, it runs 24/7 off-grid, capable of pulling 50,000 kilograms daily. After trials in the Netherlands, Jakarta became its first major real-world test during floods. Some rivers don't produce trash. They produce trash tsunamis. The Rio Motagua can push hundreds of tons of plastic downstream in hours during a flash flood. A standard interceptor can't handle that volume, so a different system was deployed. The trash fence, a barrier spanning the full river width, with poles anchored into both banks and the riverbed. The fence held most of it, but two anchor poles tilted under the surge. Bank erosion opened gaps, and a portion slipped through. The failure wasn't the fence, It was the anchoring. When water velocity doubles, barrier force doesn't double, it quadruples. The team documented every weak point. The next version would need stronger anchors, tighter bank seals, and the capacity to survive forces now finally measured. After the trash fence failure, the next design delivered. Two booms in Rio Las Vacas channeled plastic directly into extraction, pulling over 850,000 kilograms within weeks. Fine-tuning continued, but the real test loomed. Rainy season, when months of accumulated debris arrive all at once. Then the rains came. In the first major flood of the season, the Interceptor 006 caught what would become the largest single river haul ever recorded. In one night, 272 truckloads of trash, 1.4 million kilograms, were captured before reaching the Caribbean Sea. The system held. The barrier channeled the surge. What had been a yearly trash tsunami dumping millions of kilograms into the ocean was for the first time stopped at the source. The number is not just a record, it is a proof of concept at the scale the problem actually demands. Not all plastic gets caught at the river. Some escaped years ago, cycling through ocean gyres for decades. That material needs a different machine entirely. The mobile skimmer deploys two adjustable hydraulic arms that dip into open water, funneling floating debris onto a lifting conveyor and into large super sacks on deck. A marine crane swaps full bags for empty ones without interrupting collection. It doesn't replace river interceptors. It goes after what the river already let through. The Pacific is never still. Ocean basins function like interconnected highways driven by wind, Earth's rotation, temperature, and salinity differences. Circular currents known as gyres continuously trap floating material inside rotating systems. So rivers give plastic one direction to follow. The Pacific gives it millions. How do you collect waste scattered across millions of square kilometers, where waves constantly tear at equipment and one wrong net design can hurt the very marine life you are trying to protect? After repeated offshore tests successfully demonstrated proof of technology, crews returned carrying tons of recovered plastic. Conventional cleanup using ordinary ships and nets would require thousands of years and staggering costs. Instead of chasing scattered debris directly, the new approach concentrates floating plastic before extraction. System 03 became the planned full-scale blueprint for future fleets designed to operate continuously across the Pacific. Engineers now believed large-scale cleanup could finally move beyond theory and become an industrial offshore operation. Before System 03 ever entered the Pacific, someone had to prove the core idea actually worked at sea. System 002 and 800 meter floating barrier towed was that proof. The bottom stayed open so fish could pass freely underneath. Moving water naturally pushed plastic along two side wings toward a central retention zone. Once full, one vessel handed its wing to the other, freeing the second to circle back and retrieve the collected debris hauled onto deck, sorted by material, shipped to shore for recycling. 12 weeks in the water proved the system could keep up. System 03 scales that same principle into a 2.2-kilometer offshore collection structure, operating like a controlled surface flow system rather than a giant fishing net. Two long floating wings skim the upper ocean while remaining only about 4 meters deep, allowing deeper currents and marine life to pass underneath. Plastic naturally drifts along the curved barriers toward the retention zone, positioned at the rear center of the horseshoe-shaped system. Two towing vessels maintain movement at roughly 1.5 knots, slower than walking speed. Slow is an engineering decision, one that reduces bycatch and eases tension across the entire structure. Cameras continuously monitor activity inside the system, while computational teams analyze currents, waves, and density patterns to predict offshore plastic hotspots before deployments begin. After several collection days, one vessel temporarily releases its towing roll, while the second vessel secures both wings. The free vessel then approaches the retention zone from behind, lifts accumulated debris on board, sorts materials for different recycling streams, and redeploys the system for another offshore cycle. Finding plastic offshore is deceptively hard. The garbage patch spans a vast stretch of ocean, yet the debris itself is thinly scattered across it. Researchers rely on mapping systems, combining drones, AI analysis, GPS drifters, seasonal surveys, cameras, and current modeling to identify the most concentrated accumulation areas. Data from waves, river outflows, and floating movement patterns helps crews predict where cleanup systems should operate for maximum efficiency. Instead of searching blindly across millions of square kilometers, deployments target temporary offshore hotspots where ocean circulation naturally gathers debris into denser surface zones. The same research logic used for polluted rivers now guides offshore positioning decisions in the Pacific. Life aboard the cleanup vessels is physically demanding long before plastic ever reaches the deck. Crews spend weeks offshore handling knots, splicing lines, repairing nets, managing equipment, and operating through rough weather. Extraction days become the most stressful moments because the retention zone must transfer safely without losing debris back into the ocean. Sorting recovered waste is equally difficult since offshore plastic arrives mixed with ropes, damaged gear, marine growth, and unpredictable materials gathered during weeks at sea. Then came the moment proving the system could operate at meaningful scale. During one offshore extraction, crews recovered 18,360 kilograms of floating debris from the Great Pacific Garbage Patch, the largest single haul recorded during operations at that time. Massive piles of tangled plastic covered the deck as workers separated materials into recycling streams. The success created mixed emotions on board, because every successful extraction also revealed how much debris still remains circulating beyond the visible horizon. Speed alone cannot define success in offshore cleanup because the surrounding ecosystem remains extremely vulnerable. Marine animals frequently mistake floating plastic for food or become trapped inside drifting debris. Sea turtles ingest bags resembling jellyfish, and seabirds accumulate plastic inside their stomachs. Plastic never truly disappears in the ocean. Large debris gradually fragments into smaller and smaller pieces that continue circulating through marine ecosystems for decades. Microplastics move through plankton, fish, sea salt, drinking water, and eventually human food systems. Even aggressive offshore recovery cannot solve the crisis alone, because global plastic production continues rising faster than cleanup capacity. Closing the source remains as important as removing accumulated waste already trapped inside ocean gyres. Finding plastic offshore is deceptively hard. The garbage patch spans a vast stretch of ocean, yet the debris itself is thinly scattered across it. Meanwhile, the scale of the problem keeps compounding. By mid-century, global plastic production is projected to far exceed everything produced during the previous decades combined. Recycling alone cannot absorb that volume. Only 9% of all plastic ever made has actually been recycled. The real leverage lies upstream. Some companies and governments are already moving: plastic-free supermarket aisles, legislation banning single-use items, entire flight services running without disposable plastic. These are not experiments, they are proof that systems can change when pressure is sustained. Cleanup buys time. Shutting off the source is what actually ends the problem. Floating congestion is not a new problem. Long before offshore plastic cleanup systems existed, invasive water hyacinths were already choking navigation channels at ports like Stockton, California, drifting with tides and wind, reforming overnight after every harvest. Aquatic crews remove hundreds of cubic feet of vegetation per run, simply to keep shipping lanes passable. The parallel to ocean plastic is direct. Neither stays where you left it. Both redistribute constantly across large water networks, driven by currents and wind rather than human convenience. And both reveal the same uncomfortable truth: it will never fully go away. The realistic goal is not elimination, it is managing accumulation down to a level the system can absorb. Offshore plastic demands the same honest accounting. Community cleanup efforts reveal another side of the same global problem. Volunteers clearing buried canals and urban waterways show how neglected waste systems eventually push floating debris toward larger rivers and coastal zones. Plastic accumulation is not created in the middle of the Pacific. The offshore disaster begins upstream inside crowded cities, blocked drainage channels, and unmanaged dumping areas that slowly feed ocean circulation systems over time. In Mirpur, a dense district of Dhaka, volunteers uncovered something few people expected: an entire canal buried under decades of accumulated garbage. Residents had not deliberately destroyed it. They had simply run out of options: no collection infrastructure, no enforcement, no alternative, and the waterway absorbed everything until it disappeared entirely beneath the weight of daily life. Crew members dig through compressed layers of waste to reach water that had been sealed off from daylight for years. What they restore is not just a drainage channel. It is a link in a chain that, when broken, routes plastic directly into larger river systems feeding the coast. Bangladesh ranks among the most polluted countries in the world not because its people are uniquely careless, but because waste infrastructure has not kept pace with urban density. That gap is where ocean plastic is actually made. Offshore recovery vessels are working the exit. Every buried canal left uncleared keeps the entrance wide open. Even massive offshore systems cannot keep pace if uncontrolled dumping continues on land. Cleanup campaigns repeatedly return to the same conclusion: recovery operations matter, but prevention determines whether oceans actually improve long-term. Every river, canal, storm drain, and landfill connected to the sea eventually becomes part of the offshore plastic network circulating through the Pacific. If this haul ends up in a landfill, the mission merely shifts the problem from sea to land, which is why the next major challenge no longer happens on the water, but inside the recycling factory. On deck, ocean plastic is nothing like the clean, sorted material a recycling plant expects. It is wet, mixed, biologically contaminated, and chemically altered by years at sea. For an engineer, this is not raw material. It is a chemistry problem in disguise. Every cleanup operation begins with the same contradiction. Crews pull tons of debris from shorelines, yet every incoming wave delivers more. Along heavily polluted tropical coastlines, waste accumulates faster than recovery systems can process it. Fishing crews, boats, fuel, labor, and transport all become part of a growing reverse logistics chain. Plastic recovery is no longer just an environmental mission. It becomes an industrial transport problem tied to storage volume, handling cost, and material degradation. Wet plastic carries low economic value while occupying enormous space. That imbalance is what makes ocean recovery difficult to sustain long-term. The deeper challenge is not only pulling waste from the sea, but building a downstream system capable of turning damaged polymer back into usable material before contamination destroys its value entirely. Beneath calm water, recovery crews are lifting one of the strangest forms of marine waste ever dumped offshore. Millions of discarded tires were once placed underwater as an artificial reef experiment, but storms and currents eventually scattered them across the seabed. Divers now descend into a debris field where loose tires roll across coral like heavy wrecking balls, scraping and breaking living structures. Recovery is slow because every tire must be tied together underwater before lift bags can raise them to the surface. What arrives on deck is not recyclable material yet. The tires are filled with salt water, sand, algae, and marine growth that dramatically increase weight and storage volume. Every extra kilogram affects fuel consumption, deck space, and transport costs. Even before recycling begins, ocean cleanup has already become a difficult logistics operation. And sometimes, pulling the plastic out causes more damage than leaving it behind. Divers find bottles, nets, and sheets already fused into coral after years underwater, and removing them too aggressively tears the reef apart. By the time this waste reaches a sorting facility, it is no longer ordinary plastic. Sunlight, salt water, and biological growth have remade it into a contaminated mixture the ocean has spent years building. Getting plastic out of the ocean is one problem. Moving it efficiently once it's on shore is another. Wet bottles, films, and packaging consume enormous storage space while carrying little value per kilogram. Baling systems compress loose plastic into dense blocks that stack, transport, and feed into recycling networks far more efficiently. Horizontal balers automate the compression and tying process so crews handle material continuously rather than bundling waste by hand. Without compaction, transport costs alone can erase the value of recovered polymer before recycling even begins. Reverse logistics depends not just on collection, but on reducing bulk fast enough to keep vessels, warehouses, and trucks from becoming the bottleneck. Once plastic reaches land, the question shifts from how much was collected to whether any of it can actually be saved. A single recovered bottle may pass through washing, shredding, extrusion, and remanufacturing before becoming part of a new product. That process sounds straightforward until ocean exposure enters the picture. UV radiation breaks down polymer chains. Salt penetrates surfaces. Biological contamination embeds itself into textured plastic in ways that ordinary detergent cycles cannot reach. Engineers treat marine debris differently from household recycling streams for exactly this reason. Each recovered item must prove enough material integrity remains for mechanical processing. If degradation has gone too far, the polymer may no longer tolerate melting and reshaping. It becomes brittle, structurally inconsistent, or simply unusable in any application that demands strength. The workflow that turns a single bottle into something wearable runs through stages most consumers never see. Labels are stripped, adhesive is dissolved, metal components are pulled out by magnet. The plastic itself is ground into flakes, washed multiple times to remove salt and biological residue, then dried and extruded into continuous fiber thin enough to weave. That fiber eventually becomes the cord wrapped around recycled glass beads, the funding mechanism that pays for the next recovery mission. Recycling ocean plastic is not processing waste. It is attempting to rescue usable chemistry from material the ocean has spent years dismantling. Inside an industrial recycling plant, the facility behaves less like a waste processor and more like a material identification laboratory. One of Europe's largest plastic packaging sorting facilities sits in Motagua, Sweden, with the capacity to process up to 200,000 tons of plastic packaging waste annually, roughly equivalent to the amount generated by Swedish households each year. Trucks deliver compressed plastic bales that are weighed both before unloading and after, ensuring exact volume control across the entire intake. Steel wires holding each bale together are cut, and the plastic is fed onto conveyors. A shredder reduces large pieces into manageable fragments. Bag opening machines tear through collection sacks to release the material trapped inside. Powerful magnets then strip out any metal contamination accidentally mixed into the stream. What follows is a sequence of physical separations. Drum sieves divide material by size through rotating cylinders with graduated holes. Ballistic separators use vibration to send heavy, rigid plastics downward while pushing light, flexible film upward. Wind shifters use directed airflow to pull soft plastic away from harder fractions. The heart of the plant is optical sorting. 19 near-infrared sensors scan polymer signatures at high speed, identifying each material type and color in fractions of a second. The scanning process runs multiple times to maximize purity, producing 10 distinct polymer categories: PP, HDPE, PET, and others, each compacted into new bales for transfer to manufacturers who wash, grind, and pelletize them into recycled feedstock. A single wrong polymer in the wrong stream can collapse the value of everything around it. Optical sorting systems spread bottles evenly across conveyor belts before sensors identify target materials and air jets eject unwanted fractions. Multiple sorting passes progressively purify clear PET and strip out contaminants. These systems perform well with controlled, consistent waste streams. Ocean plastic disrupts that consistency. Sun bleaching, abrasion, biofouling, and surface discoloration make damaged material harder for sensors to classify correctly. Maintaining polymer purity is not optional. Recycled material loses market value rapidly the moment incompatible plastics enter the stream. Infrared and color sorting systems remove PVC, PS, PC, and other incompatible plastics from PET streams. Ultraviolet systems can identify aged PET flakes that behave differently during reprocessing. These technologies matter because marine waste almost never arrives as a single clean polymer. Mixed materials, faded surfaces. Washing ocean plastic is not comparable to rinsing a bottle collected from a curbside bin. Every grain of salt left behind becomes a threat to the machinery downstream. Film washing systems for LLDPE and LDPE show how aggressively contaminated plastic must be treated before it can re-enter production. Agricultural films and post-consumer sheets arrive mixed with dirt, moisture, and organic residue. Washing lines shred the material, separate contaminants, squeeze excess water, and reduce moisture content before extrusion. Ocean plastic arrives in even harsher condition. Biofouling and prolonged saltwater exposure accelerate chemical degradation throughout the polymer structure. Every remaining impurity increases mechanical wear and reduces pellet consistency. Contamination removed early protects everything that comes after. PET is the world's most recycled plastic, and watching a single bottle move through an industrial recycling plant explains why the material earned that distinction. In Europe alone, billions of plastic bottles are bought and thrown away every year, and most of them are made from PET, a polymer that happens to be easy to collect, sort, and reprocess. Bales of collected bottles arrive at the facility and are cut loose onto conveyor belts. Magnets remove metal contamination. A pre-washing stage strips labels and adhesive. Optical sorting separates non-PET materials, and manual sorting catches whatever the machines miss. A grinder then reduces the bottles to flakes, which pass through additional sorting by material type and color. The flakes enter a silo, are dried, melted, and filtered, then extruded as continuous strands, spaghetti, of reformed PET before being cut into pellets. A decontamination unit running under nitrogen brings those pellets to food-approved standard. One plant in eastern France processes approximately 4 million bottles per day. The material is made to be remade. When plastic is too damaged for mechanical recycling, the answer is not to melt it. It is to break it apart almost to the molecular level. Pyrolysis heats plastic in low-oxygen environments at extremely high temperatures, decomposing polymer chains into synthetic oil and chemical feedstock. The technology handles material that would otherwise be unrecoverable multi-layer packaging, heavily fouled ocean plastic, mixed polymer streams that optical sorting cannot cleanly separate. Its limitations are real. Energy consumption is significant, emissions control is technically demanding, and output quality varies with input consistency. Discarded fishing nets or ghost nets recovered from the ocean often contain nylon polymers that retain material value after cleaning. The nets are shredded, melted, cooled into strands, dried and pelletized into uniform recycled granules that can re-enter industrial production rather than continuing to trap wildlife on the seafloor. Successful pellet output depends heavily on contamination control. Excess salt, sand, or mixed polymers can destabilize extrusion and degrade pellet quality throughout the run. Recycled nylon produced from recovered gear can be transformed into textile products after extensive purification and reprocessing. Because nylon holds stronger material properties than most packaging plastics, it can support more expensive recovery systems economically. Growing demand for ocean-source textile feedstock has shifted interest specifically toward fishing gear recovery rather than treating all marine debris as interchangeable material. What an industrial-scale plastic recovery operation looks like from the inside is rarely shown, and the scale of what arrives before any cleaning begins is striking. Compressed bales arrive by truck and forklift, stacking in outdoor yards before entering the facility. Rotating drums, strip dust, and fine contamination in the first pass. Manual sorting lines staffed largely by local workers pull non-conforming materials directly from the belt. A label removal drum tears adhesive and paper off bottle surfaces. Twin screw processing cleans the material at a deeper level. The output white translucent flakes is dried, inspected, and packed into large bags as high-quality recycled feedstock ready for fiber production. Recovered flakes and pellets can move beyond packaging into textile manufacturing. Melted polymer passes through spinnerets, forming ultra-thin filaments before stretching and heat treatment build material strength. Some fibers are cut into staple form and compressed into bales for later spinning. Others feed directly into yarn systems. The process shows how recycled polymer chains can re-enter industrial production, though maintaining fiber consistency becomes progressively harder when source material arrives heavily degraded or mixed across polymer types. Once recovered, ocean material enters the fashion supply chain. The engineering story stops being anonymous. It gets a brand name and a retail price. The first Adidas X Parley shoe was built from gill net intercepted during an illegal fishing enforcement mission. The net was spun into yarn and woven straight into the shoe's upper, skipping cut-and-sew waste entirely. In 1 year, the network behind it intercepted 746 tons of marine debris. The shoe is not a solution to ocean plastic. It is evidence that recovered marine material can hold enough value, technical, commercial, and reputational, to justify the entire chain that brought it there. What if the factory came to the ocean instead of the other way around? Some systems now process marine waste close to where it is intercepted rather than shipping everything across the world first. Modular recovery stations sort, clean, and process plastic directly on remote islands and coastlines. Recovered material can be upcycled into printed structures, furniture, or local manufacturing feedstock on site. Localized processing cuts transport emissions and prevents waste from re-entering ecosystems during long logistics routes. It also signals a broader strategic shift, building circular material systems near the source of pollution rather than depending entirely on distant industrial infrastructure. From here on, ocean plastic takes a new form, the only one consumers ever see. Textile facilities transform recycled yarn into finished fabrics, knitted rolls, and eventually clothing. Modern knitting systems produce smooth material from polymer, once drifting as marine debris. Surface finishing and quality inspection prepare textiles for fashion and industrial applications. The visual transformation from contaminated ocean waste to wearable fabric is stark, but it conceals the sorting, washing, drying, and stabilization work that made it possible at every earlier stage of the chain. A river barrier capturing 35,000 pounds of trash during one storm sounds like a win, until you realize the next storm is already forming offshore. The deeper question starts here. What happens when the machines work exactly as intended, yet the stream of waste still keeps coming? Along Bottleneck Creek in Los Angeles County, Interceptors 007 entered its first heavy rain season as part of a 2-year pilot program designed to test how much floating debris could be stopped before reaching the Pacific. Operators deployed a second boom before the rain arrived because storm flow changes by the hour. The system pinned massive clusters of floating waste against a guiding barrier, with each onboard container holding up to 12,000 pounds per rain event. Early leaks along one side of the barrier revealed a problem that simulations could not fully predict. Water levels changed with the tide, and the gap between the levee and the boom widened and narrowed accordingly, creating openings large enough for trash to slip through during higher tides. Crews quickly repurposed older containment booms from another location, connecting them to the end of the barrier and running them parallel to the levee to close the gap. Everyone could see that the machine worked. But everyone could also see how much trash still existed upstream, waiting for the next storm to push it down. The most revealing moment was not the amount captured. It was the realization that crews had expected 6 collection loads across the entire year, but were already working on their 3rd load during the first rain event alone. The machine succeeded technically. The scale of the waste stream remained overwhelming. And the numbers behind global plastics still tell a harder story. Modern recycling systems attempt to pull material back into production instead of allowing it to be buried, burned, or lost in waterways. Mechanical recycling works well for cleaner, more uniform plastics bottles and rigid containers. Mixed films, fibers, and contaminated materials are far more difficult. Those streams often require pyrolysis, where heat breaks polymers back into molecular feedstock. The challenge is scale. Global plastic production continues rising, while only a small fraction is recycled effectively. Even advanced recycling plants depend on careful sorting and relatively stable feedstock quality. Ocean plastic rarely arrives in that condition. Salt, sunlight, biological contamination, and polymer mixing reduce both processing efficiency and economic value before the material even enters the facility. What happens after collection determines whether cleanup becomes a circular system or just an expensive relocation project. At large recycling facilities, truckloads of discarded plastic films arrive daily from household and industrial streams. The material moves through sorting by origin, polymer type and color, washing to remove labels and residue, then extrusion into clean granules under tight quality control. The volume is not fading, it is the steady output of a system that keeps generating plastic faster than cleanup operations can remove it. That gap is what makes circular recycling both necessary and insufficient on its own. The process makes one argument clearly. The material itself is not automatically the problem. When properly separated and processed, plastic that once appeared worthless can displace part of virgin polymer demand. But this model requires enormous infrastructure, energy, transport logistics, washing systems, computerized controls, and constant material input. It works best when feedstock is predictable and relatively clean. Ocean plastic is neither. By the time material reaches open water, the cost of restoring it to usable condition has already risen dramatically. System 03 pushes ocean cleanup into territory that had not been tested before. Engineers shifted focus to full-scale systems built for continuous operation across the Great Pacific Garbage Patch. No amount of cleanup footage can fully capture the scale of that reality. These machines are evidence of how expensive unmanaged waste eventually becomes. So where does the real bottleneck sit? In the collection technology, in the cost of recycling, or in the responsibility of the companies putting this plastic into the world to begin with? Leave your take in the comments. If you like that we don't stop at the machine but pull apart the engineering system standing behind it, subscribe to You Can Do TV. Here, we don't just watch giant machines operate, we break down why they had to exist in the first place. Thanks for watching. See you in the next one.